we're going to continue talking about drawing Lewis structures. This one is going to focus on drawing the Lewis structures of oxyanions, polyatomic ions containing oxygen. Okay, we'll focus first on the carbonate ion. Right, again, right, carbon is less electronegative than oxygen, so carbon would go in the center of our connected structure. Right? If we look at our valence electrons, carbon contributes 4, 3 oxygens would contribute 3 times 6. Right? That's 4. That's 18 is 22. But we have the negative charge, so we have to add 2 more electrons for the 2 negative charges, meaning we're talking about distributing 24 valence electrons. We've already accounted for 6 of those because of the bonds we've already drawn, leaving 18. We start around the outside, distributing electrons in pairs. Now we're out of electrons, but our central atom does not have an octet. And if we check our formal charges, each oxygen has a negative charge and the carbon has a positive charge. And so we can, right, to at least get rid of the formal charge on the carbon, we can bring in a pair of electrons from one of the oxygens. And so we can end up with a double bond to that oxygen. Still a single bond and unshared pairs there. Right? And if we do our formal charge analysis, we see that negative charges appear on the oxygens. That's acceptable because oxygen is more electronegative than carbon. So if anything's going to be negative, it will need to be oxygen. And the total number of the total of the formal charges equals the total charge on the ion. So that is an acceptable structure. Now, one thing you might ask, right? Does it make a difference if we pick a pair of electrons there, or a pair of electrons there, or a pair of electrons there? Right? We can draw each of those structures. So if we pick the red arrow, we get something like this. Unshared pairs, negative charge on that oxygen. Negative charge on that oxygen. If we pick the white arrow, right, that's going to put our double bond there. And then these oxygens still have their unshared pairs. Right? So really we have 3 acceptable and equivalent Lewis structures. When we have multiple acceptable Lewis structures for a chemical species like this, that's where we have the opportunity for something called resonance. Right? Really, all of these Lewis structures are valid. And so we can say we can interconvert these by using a double-headed arrow, right? That designates that those are resonance structures of each other, right? And so the real structure is really an average of all of these structures. But when we're drawing Lewis structures, we sort of have to pick one, right? And so we know that all of these contribute to the overall structure of the carbonate ion. So we have multiple resonance structures for the carbonate ion. So now let's consider the Lewis structure of the NO3 minus, the nitrate ion. Right? So again, oxygen is the more electronegative, so that's going to push the nitrogen to the center. Right? With oxygens attached. If we look at our valence electrons, right? Nitrogen will contribute 5. The 3 oxygens will contribute 3 times 6. So that's going to be 5 and 18 is 23. But we have to remember that there is a negative charge. So we have to add 1 electron for the negative charge, giving us 24. Right? We already have 3 bonds accounted for. That's 6 electrons, leaving us with 18 to distribute. Distribute those around the oxygens. And we get a structure like that, right? We're out of electrons now. And so we don't have to distribute any more electrons, but we can see that the central nitrogen only has 2, 4, 6 electrons around it, right? We have any of these oxygens could share another pair of electrons with the central nitrogen. Right? So if we drew all those, we would expect to have multiple resonance structures. Right? So let's pick, since I drew with blue, let's go with the blue choice. So we end up with O, O, O. Right? Now if we look here, if we do our formal charge analysis, the formal charge on each oxygen here is negative, and this one is 0. And the formal charge on the central nitrogen is positive. Right? So in this case, everything has an octet, but 3 of our 4 atoms have formal charges. Now, 2 negatives and 1 plus, that adds up to the 1 negative we have there. Right? So in this case, even though we have 3 atoms that are charged, the central nitrogen is the less electronegative atom, so it can have a positive charge. The oxygens can carry the negative charge. And we have multiple resonance structures, so there would be 2 more equivalent structures like this, right? So that the negative charge is really shared among all 3 oxygens. So there is the Lewis structure of the nitrate ion. Our next ion to consider is the phosphate ion. right? So if we draw this again, oxygen is more electronegative, so oxygen goes around the outside. Phosphorus has to be the central atom, right? If we look at our valence electrons, right? Phosphorus brings 5. 4 oxygens brings 4 times 6. So that's 5. And 24 gives us 29. But we have 3 negative charges, so we have to add 3 electrons for our negative charges, giving us 32, right? But we already have 4 bonds drawn. 4 bonds times 2 electrons for bonds is 8, leaving us 24 electrons to distribute. One, 22, 23, 24, right? We're done. And everything has an octet. So you might think we're done. But we always have to go back and look at the formal charge question. Right? If we calculate the formal charges for each atom, each oxygen has a negative formal charge, and the central phosphorus has a positive formal charge. Now with nitrogen, when it had a positive formal charge, we had to leave it there because we couldn't give it any more electrons. It already had its maximum of 8. Remember, phosphorus is in that third period. It can accommodate more than 8 electrons. And so, again, one of the things we can do is, and in this case, pick an oxygen because we could use any of them. I'm going to pick the one on the left here, partly because there's space. We can drop that pair of electrons into there, share it that pair between the 2 atoms, and so we can end up then with this kind of structure. Right, where this oxygen has only 2 unshared pairs. The other ones still have 3. Right? And these still have a negative formal charge, but at least 2 of these atoms have no charge. And again, we could have done this with any of these 4 oxygens. So we know that there will be 3 more equivalent resonance structures if we wanted to draw them, right? And so we make these, in this case, we're making this double bond, or adding this second bond here to give at least 2 of the atoms a 0 formal charge, leaving the 3 oxygens, again, the more electronegative atom is going to carry the negative charges that are there. And the 3 negative charges add up to the overall charge on the species. So there is the Lewis structure of the phosphate ion. Now we'll consider the SO3 2-, or the sulfite ion. Okay? And again, sulfur is the less electronegative of the 2, so it will have to go to the center of the structure. We'll have to consider our valence electrons. Right, I'll try to move this over a little bit. So sulfur will contribute 6. 3 oxygens will contribute 3 times 6. So that's 6. That's 18, giving us 24. But this has a charge. Right? We have 2 negative charges. So we have to add 2 more for the negative charge, giving us 26. But we've already accounted for 6 of those because of the bonds we already have there, leaving us with 20 to distribute. We start around the outside, right? Starting with the oxygens, distributing them as pairs until each oxygen has 8. That's 18, 19, 20. Right? Now at this point, everything has an octet. We might think we're done, but remember, we're not done until we consider the formal charges, right? When we consider the formal charges, each of those oxygens has a negative formal charge. The sulfur in the center has a positive formal charge, right? And so, if possible, we like to eliminate the formal charges. We can pick any of our oxygens, right? They're all equivalent. So we'll pick that one, right? So if we drop a pair of electrons in there, then we can redraw our structure. Right there, 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 with a negative charge on those 2 atoms, no formal charge on those 2. And I have to remember, right, this sulfur still has the unshared pair we put on it originally. And that would be an acceptable structure. And again, we could have done this with either of these 2 oxygens. So we have to be aware that there are 2 more resonance structures that we could draw for the sulfite ion. All right? And now we will consider the example of the iodide ion. Right? The iodide ion. Now with the iodide ion, right, we've got the iodine in the center, 2 oxygens. Right? Again, we consider our valence electrons. Iodine brings 7, 2 oxygens brings 6 each. That's 7 and 12 gives us 19. But we have a negative charge, right? The negative charge means we have to add 1, right, for that negative charge. Gives us 20. We have already accounted for 4 of those because of the 2 bonds we've already drawn, leaving us with 16, right? So we start around the outside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Right? Now we have distributed all of our valence electrons. Again, it looks like everything has an octet. right? We're tempted to be content with that, but if we look at our formal charge calculations, right, each of the oxygens is negative. The iodine in the center has a positive formal charge. And so again, right, because iodine is in the third period or larger, it can accept more than 8 electrons. So if we drop a pair of electrons in from one of the oxygens, we get a Lewis structure that looks like this. Right? We get a double bond to an oxygen. The other oxygen, this oxygen has all of its unshared pairs. This oxygen still has 2 of its unshared pairs. The iodine and the negative formal charge is on the oxygen. And again, iodine can exceed the octet because it is larger and has more space for electrons, right? And we have to remember we could have done the same thing with the other oxygen, and so there would be one more stable equivalent resonance structure that we could have drawn, right? So there's some examples of drawing Lewis structures of the polyatomic oxyanions.